Everyone, my name is Adi, and I'm from the Bar-Ilan University in Israel, and I'm going to speak today about new deposition method for tunable band gaps for lead-free halide perovskites in films with improved stability. Okay. So as we all know, silicon modules are the most common materials for solar cells today, and with the high production of the silicon material, the price has decreased. Yet we still have an efficiency. The efficiency hasn't improved in the past few years, and it's very close to its theoretical limit. This is an efficiency chart. So a solar cell is estimated by its efficiency. It's got a lot of information here. But if we look, and we'll look a bit closely in a minute, but if we look in the general, we see that the blue lines correlate for silicon solar cells that have been investigated since 1970. And here in yellow and red line, we see the halide perovskite that have been studied since 2012. We look a bit closer, we'll see the numbers. So we have the organic solar cells that are already achieving 18% efficiency. We have the halide perovskite very close to the silicon with 25% efficiency. Silicon best cell has a 27% efficiency. We also have the gallium arsenide with 29%, which is used only in space. And we have a new type of solar cells, which is the tandem solar cells. That is a multi-junction solar cells usually used with silicon and halide perovskite. I'll show in a minute a bit more about it. And it has a very recently new record of 30.9, and it's improving very fast in the last few years. So the tandem solar cells are, as I said, multi-junction solar cells. It's basically more than one solar cell in a stack, where the bottom cell is usually used by silicon that absorb a small part of the solar spectrum, and by putting another solar cells that can absorb a different part of the solar spectrum, we can harvest more photons per area. So a bit about the halide perovskite, and the top cell is usually, I forgot to say here that the top cell is usually the halide perovskite is used today. So a little bit about halide perovskite. They have the formula of ABX3, where X is the halide, chloride, bromide, or iodide. The A is a +1 cation, cesium, inorganic cesium, or organic molecules such as methylammonium and formidinium. And on the B side, we have the lead +2, which achieves the high efficiency as we talked about. But not only, it has a tunable band gap of 1.2 and 3, between 1.2 and 3.2 electron volt. It has very high absorption coefficient for a very thin layer, high charge carrier mobility, long diffusion length. And the most important thing is that those materials are cheap and simple to prepare. Solution-based methods such as spin coating for highly crystalline thin film. The main problem with halide perovskite is they contain lead, and lead is toxic, so it's a very limiting factor for commercialization. And the solution is to replace the lead with tin or germanium. This is what we do in this work. But many other groups are studying many other metals for replacement of lead. So a little bit about the tin-based halide perovskite. They have a very small band gap, which is very suitable for solar cells. yet they're not stable. Tin plus 2 is not stable in the plus 2 oxidation state and tends to oxidize to the plus 4 oxidation state, causing the fast degradation of the material and, of course, the solar cell performance, as we can see in this paper. When you go to the germanium-based halide perovskite, most of them are prepared with iodine, and we have only very, very few experimental papers regarding the germanium-based halide perovskite. And I think that the main problem with them is that they have a very low solubility, and with the current deposition techniques that we use today, such as spin coating, a very low concentration solution is very hard to work with. So in this work, we fabricate for the first time cesium germanium tin bromide. So germanium and tin are just above lead in the periodic table and assumed to have similar properties and high potential to replace lead. Both cesium and bromide are chosen because they are considered to be more stable than the organic molecules or iodine. And when we choose atoms or elements to construct this structure, we need to think about the size. So both germanium and tin are smaller than lead and therefore require smaller atoms in the structure to make it stable. Stability is defined by the Goldschmidt tolerance factor, which is basically a relationship between the atomic radius of the A, B, and X elements. For cesium tin bromide, the tolerance factor is 0.9. For cesium germanium bromide, the tolerance factor is 1. And it's assumed to be more stable, moving closer to 1. Bandgap tuning is possible between 1.8 for the cesium tin bromide, the pure cesium tin bromide, and 2.5 for the pure cesium germanium bromide. So due to the low solubility of those materials, we decided that we need to work with them, and we just need to find a different deposition method that can work with the low concentration solution. And that's where we decided to go for a 3-nozzle spray deposition that was built especially for this purpose, together with Dr. Shai Tirosh from my lab. So the main idea is that we can spray low concentration solutions. The spray is located inside a dry box filled with nitrogen, so the environment of the deposition is without oxygen and humidity. And basically we have a control over the temperature, the flow rate, the volume, and the concentration of the deposition. So at first we tried to compare the deposition of spray, the same solution, sprayed and spin coated. We see for the sprayed film, we see a good coverage, more or less good coverage. Particles are connected to each other. When we look at the spin coated film, we see particles that are disconnected from each other. We see more or less just the substrate. And if we look also at the absorption spectrum of those two films, we see a much higher intensity for the sprayed solution and a very low intensity for the spin coated due to the poor coverage. So after we established the deposition method, we decided to try to fabricate the 5 different compounds. So we sprayed the cesium tin bromide and the cesium germanium bromide and 3 compounds in between with different ratios of germanium and tin. We performed the absorption measurement, optical measurements for the 5 samples. And from the optical absorption, we could calculate the band gap that correlates well with literature for the pure compounds, 1.8 for the pure tin and 2.5 for the pure germanium. And the 3 compounds have a tunable band gap in between those 2 values. From XRD measurements, we see good crystallinity of those film. We do see for the pure tin compound, we see a cubic structure that correlates good with literature, and for the germanium, we see a triagonal structure, and the 3 compound solid solution compounds in between have adopt the cubic structure. We see here a small shift of the 2 theta with increasing germanium, which indicates that the germanium does incorporate in the structure and change the bond length. We calculated the bond length, the B2B bond length. It's either tin germanium to tin germanium length, to see if it fits the linear law of Vigard, and we do see a good linear fit with regard to the concentrations. The concentrations are measured by ICP for the sprayed solution. When we're talking about material for solar cell, we want to know a bit about the energy alignment of those systems. So we perform photoemission yield spectroscopy measurements to measure the ionization energy of those materials that reflects the valence band position. We see that with increasing concentration of germanium, we have an increase in ionization energy, meaning deeper valence band. And that's because the hybridization changes from 5s to 4s of germanium, making the ionization energy higher. We plotted here, this is the bottom one is the valence band with respect to the vacuum, which is 0. We calculated the conduction band from the band gaps, and we have the Fermi level from the CPD measurements using Kelvin probe. We wanted to understand, before we implemented in a solar cell, we wanted to understand a little bit more about the stability of those materials and how they affect each other. And we performed XPS measurements, which are surface sensitive measurements, on 5 fresh samples and on 5 samples that were left in the glove box, nitrogen glove box, for a week. And we wanted to see if we have a shift of the binding energy that will indicate that we have a change in the oxidation state. And we indeed, so in this plot, we have the change of the shift in binding energy. We see that for high concentration of germanium, we have almost no shift in binding energy position, indicating no oxidation. And when we move to high concentration of tin, we see oxidation of both tin and germanium to higher oxidation states. Again, it's indicating degradation of the materials that will eventually degrade the solar cell. Also from the XPS, we noticed that we have the peaks, the germanium peaks have very high intensity, even though the concentration is decreasing, the intensity is very high. And we found that we have high concentration of germanium on the surface of those materials. The thin films have high concentration on the top of germanium that assume to protect the film from further oxidation. We tried to implement it in a solar cell. So we used the 51% germanium. In a stack, we have a few different layers that all together form a solar cell. And we found out that we have very low efficiency and very low currents with about 350 millivolts VOC. And we try to do a different measurement to see, we think this is because we still have holes in the film. The film is incomplete, and those holes create shorts, and therefore we don't have much current. So we try to characterize it using surface photovoltage, which is a contactless measurement. We have a vibrating tip from a Kelvin probe. The stack is much smaller, so it's only half a cell, and we measure contact potential difference in the dark and in the light, and we see the photoactivity of this material. And so we see very high response for the something here changed. For the 100% germanium, we see a very good response with about 550 millivolts change. It's Fermi level splitting change, which is considerably very good for very new materials that haven't been explored before. And it indicates a very good potential. If we can get a complete coverage, we can actually make quite a good solar cell with those materials. So to conclude, I showed you a new spray deposition technique that overcoming the solubility problem of germanium-based precursors. We saw that with increasing concentration of germanium, it stabilizes both the tin 2+ and the germanium 2+. Germanium is forming capping layer that stabilizes the film and protects it from oxidation. And we have a high availability as absorber material for photovoltaics applications. And the next step will be actually to optimize and to improve the coverage. As I said before, those materials are very new and have very high potential, but needs a lot of optimization and further work. So I want to thank you all, and I want to thank Professor David Kain, Dr. Shai Tirosh, and Anat Yitzhak, and thank you all.